Hello and welcome back. Today I want to talk about the three basic non-isolated switch mode power supplies. The buck, the boost and the inverting buck-boost. Now I don't want to go into any of the mathematics behind them, that's a topic for a different time, although if you're curious I will leave a link to this document in the description. I just want to analyze the basic operating principles. How do these power supplies work? So if you're curious, then keep watching. Now, the first thing to discuss is how the components that make up the power supply work. So this will be just a short review of how the capacitor and the inductor are used to store energy and transform it. So let's start simple. We got capacitors. And let's analyze this component in two stages. So when the capacitor is charging and when it is discharging. So when it's charging, it works like a load. It takes energy from the system. And during charging, the voltage on the capacitor will rise, and we can say that the current is positive. Current is going into the capacitor. Now when the capacitor is discharging, it turns from a load into a generator, meaning that it is giving energy to the system. Now in this stage, the voltage on the capacitor will decrease, and if the current going into the capacitor during charging was positive, then the current will be negative, since it will be going into a different direction. Now another thing to look at is the current to voltage relation. We can determine how fast the capacitor is charging or discharging based on the current that is applied and the capacitance of the capacitor. So with this relation we can find out how much time it will take to charge a certain capacitor to a certain voltage when a certain current is applied. So if we think of our capacitor in the two stages, we will have first the charging stage when we charge it with certain current. This time the capacitor works like a load. We charge it with certain voltage. And then when we discharge the capacitor, the voltage stays the same, but the current now goes in a different direction into a certain load. So this time the capacitor is a generator. So the first time it was a load, second time it's a generator. Now if we would graph this out on a plot, so we got voltage and we got current over time. If we apply a positive current to the capacitor, the voltage on it will rise. If we stop applying current, voltage will stabilize. And if we draw current from it, so a negative current goes in the different direction, then the voltage will decrease. So this is quite easy to understand, easy to test out. But now let's look at the inductor, since this is the second major component used in a power supply. Now what's special about the inductor in relation to the capacitor is that it works exactly the same. The only difference is we will swap the currents and the voltages. So when we're charging the inductor, the current will rise and the voltage will be positive. When we're discharging the inductor, so when we're using it as a generator, the current will fall and the voltage will be negative. Now we have a similar current to voltage relation for the inductor, and it goes a little something like this. The rate of change of current through the inductor, so how much it rises or how much it falls, depends on the applied voltage and the inductance value. So this time we will apply a voltage, so a voltage source is applied to the inductor. We will have a certain current going through it and certain voltage applied. Now when we use the same inductor as a generator, the direction of the current will stay the same, but the voltage changes. So if we first had plus minus, in the second case we have minus plus. And this is in the case we're using it as a generator to power a certain load. Now the same graphs are similar for the inductor, but this time we swap the current with the voltage. So that means if we apply certain voltage to the inductor, the current rises. So it doesn't jump, it rises linearly. If we stop applying a voltage, current stays the same. So if we keep the voltage between the two pins of an ideal inductor at 0, then the current will stay the same. And then when we apply negative voltage, the current will decrease. So the inductor will be working like a generator. So let's see this behavior in a simulation just to make it a bit more clear. So what I got here is the basic circuit that I've drawn a moment ago. I've got a current source that will charge a capacitor and a voltage source to charge an inductor. And I use the PVL type of source. So let's just see this thing in action. So you can see that our current source first has a positive current, stabilizes at 0, and then has a negative current. And if we check the voltage on our capacitor, we can see that in the first stage it's charging, in the second stage the voltage is stable, and then in the third stage it's discharging and going back down to 0 volts. And the exact same thing happens with our inductor. So we have our voltage source this time, a positive 1 volt, then 0 volts, then -1, and we can see that the current going through the inductor starts from 0, goes up to 1 amp, stabilizes at 1 amp, and then goes back down to 0 amps. One of the things to mention regarding the two sources, in the case of the inductor, the 0 volts corresponds to a short circuit, so the inductor is being short-circuited and the current on it stabilizes, whereas for the current source, when we have the current at 0 amps, we're simulating an open circuit, so there's no current going through the capacitor. So let's start our analysis of power supplies by looking at the buck converter. So this is what our basic buck converter looks like. We got our input voltage, input and output capacitor, a diode, a switch, and an inductor. And then we have the load on the output. Now we can analyze two phases in regards to this switch. So when it's closed, like this one, and when it's open, like we got here. So let's see how the current will be going through our circuit in the two cases. So let's start with the first one, switch is closed. So we got current going from our first capacitor, charged with a voltage. Current will be going through our inductor, charging our second capacitor, and also going through our output load. So this will be the direction of the current, and this will charge our inductor with a certain current, so we will have a certain voltage on it, and then we will have a certain voltage also on our second capacitor. Now in this case, our C1 is a generator, our inductor is a load, our second capacitor is also a load, and the load is, well, a load. Now let's see what happens when we turn to the open switch. This time there will be no more energy coming from our input capacitor, and now the devices that have been loaded with energy, so our inductor and our capacitor, will turn from loads to generators. So let's see how that happens. So our capacitor will maintain its polarity, nothing will happen, but since in our first case current was going in this direction, now the current will be going in the other direction. The same for our inductor. We said that the direction of the current stays the same, so just like in our initial case, but the voltage on it will be different. So these will be our two generators this time. Now the current going into this node will come out the other way, so it will be going through our resistor load. We have one loop that discharges our capacitor into our resistor, and we got our second loop that discharges the inductor into the resistor and closes through our diode. Now you may know that the buck converter is a converter whose output voltage is lower than the input voltage. But why would that happen? Well, let's have a look at our first case. So if we would apply Kirchhoff's voltage law on this circuit, we can say that the voltage on our generators, so the voltage on C1, which is actually the input voltage, is equal to the voltage drop on the loads, which is the voltage on our inductor plus the voltage on our load, which is also the output voltage. Now since the voltage on our inductor is a positive value, that means that no matter what we do, the output voltage will be lower than our input voltage. So our input voltage will be higher than our output. In the same way, if we look at the second case, since our capacitor is now a generator, the voltage on it will drop. So whatever voltage was on our load to begin with, our initial output voltage, our second output voltage, so in our second stage, can only be slightly lower than that. So in this case, we cannot have a higher output voltage. In practice, the output voltage in both cases will stay roughly the same, always being smaller than the input. And by how much it's smaller than the input will depend on the time spent charging the inductor and the capacitor. Basically, that's how the buck converter works. So let's have a look at this circuit also in a simulation, just to make sure that we got all our currents and voltages right. So this is the basic buck circuit that I'm going to show you. We've got our input supply and an input capacitor, output capacitor and load, the inductor, the diode, and the switch transistor, and of course some circuitry to help drive it. So let's see how this thing works. We can look at the voltage coming into our transistor, so when this voltage is high, the switch is on, when it's low, the switch is off, we can see the current that's being drawn from the input is rising only when the switch is on, so when the switch is off there's no current, and we can see that the current drawn is in a ramp. Now this ramp is because of the effect of our inductor. So if we look at the current for the inductor, we can see that the current being drawn from our supply on this rising slope is exactly the current going into the inductor. So this input current only goes into our inductor. Now there's one thing I failed to mention when I analyzed the switching on and off states, and I did this intentionally to keep the explanation a bit simpler. But now when we look at the waveforms, we can clearly see that we have a bit of an issue with the current going through our capacitor. Now since we have a resistive load at fixed voltage, the current through the load is fixed, but the current going through the inductor is sometimes higher, sometimes lower than our output current. And this is where our capacitor comes into play. Now because of the way Spice just showed this, it's a bit in reverse, so it should look something like this. So what we can see here is that when our inductor current is higher than our output current, the rest of the current is going into the capacitor. So the capacitor is absorbing all of this extra current from the inductor. In the same way, when the inductor current is lower than the output current, the capacitor is providing the rest of the current needed. So the sum of the inductor and the capacitor current is the output current. So our capacitor is working like a load when the inductor current is higher than our output current. So half of the on time, half of the off time, the capacitor is the load. And then the capacitor is a generator when our inductor current is lower than the output current. So the other half of the off time and the other half of the on time. This way we can stabilize the output voltage and the output current. Now there's one more thing to check with the Buck circuit, and that's the ratio of input to output voltages. So we can see that our output voltage is around 5 volts and our input voltage is 10. So our output voltage is lower than our input voltage. Also we can look at one of the things that makes switching supplies so common nowadays. That is the efficiency. So we can look at the output power, around 2.5 watts, and the input power, which we have an average of 2.8 watts. So very high amount of the input power is actually getting to the output. The rest of it is being lost on the diode and our switching circuit. So if you make these a bit more efficient, then you can have a much higher energy transfer rate from input to output. And you have a very good efficiency because of the way you're transforming the energy. So you're storing it either as a magnetic field in the inductor or as an electric field in the capacitor. Both of these components, if they are ideal, they have zero losses. Now in practice they will have some loss, but you can design quite efficient circuitry if you really put your mind to it. Now all the simulations that I'm going to show you today can be found in the description below, so if you want to play around with them, check them out a bit in more detail, just have a look and click the link. So let's move on. Now let's perform a similar analysis also on the boost converter. So we basically have the same components like in our buck converter, but the way they are arranged is a bit different. So we got our input voltage, input capacitor, output capacitor, load and output voltage, and then we have an inductor and a diode and the switch, which again we will analyze in two cases, once when the switch is closed, once when the switch is open. So let's start with the first case. Again, our C1 is our generator, so this will be providing energy to the system, and the current from it will go through the inductor, charging it, so the inductor will be a load, and the current will close through our switch. Voltage will have this polarity on our inductor. Now the moment the switch opens, our input capacitor will remain a generator, since it's always applied from the input. Our inductor will turn from a load into a generator, and this time our load and second capacitor will become our actual loads. So the current through the inductor will keep the same direction. The current through our input capacitor will keep the same direction, since it went from generator to generator. So the voltage on it will stay the same, the direction of the current stays the same. The voltage on the inductor changes this time, since it went from load to generator. And this current goes through the diode, charging our second capacitor and supplying the load. And then it closes back. Since we've charged our second capacitor, we can go back a bit to our first case, where our second capacitor is charged during the open switch phase. So in the closed switch phase, our second capacitor will actually be a generator, it will be charged with a positive and negative voltage, and the direction of the current will change. So in both cases our load is supplied, so even when the switch is open, even when it's closed, once from the input and once from the output capacitor. Now let's analyze a bit the output voltage. How is it in relationship to our input voltage? Well, we can look at this situation. Let's look at our generators and our loads. We have two generators, C1 capacitor, which also has the same voltage on it as our input voltage. We have in series with it another generator, our inductor, so we will have a voltage on our inductor, and this sum will be equal to the voltage on our load, so our output voltage, plus the voltage on the diode, which can, let's say, be neglected for the purpose of this exercise. That means, since our inductor voltage is higher than 0, that our input voltage will be smaller than our output voltage, since our output voltage is the input voltage plus something. That is why our boost converter will always output a higher voltage than the input. And depending on how much time you've spent charging the inductor in the first phase, the output voltage will be higher and higher. So let's have a look at this converter also in a simulation. So here I have a boost circuit. Again, I'm supplying from 10 volts. I've got my input capacitor, an inductor, diode, output capacitor, and load resistor, and a switch with a driving circuit. So let's see how this thing works. So again, we can see the current through the inductor, when the switch is on and when the switch is off. So when our switch is on, the inductor is charging. When the switch is off, the inductor is discharging. We can also see the current being drawn from our input supply is exactly the same current that's going through our inductor. And we can see that the current going through the output load is constant. Now let's see what the capacitor does this time. So now if we analyze the on and off stages of the transistor, we can see that in the on stage, the inductor is being charged from the input source, and the output load, so this cyan color or whatever it is completely supplied from the output capacitor. So we can see that the pink and the cyan are exactly the same value during the on stage. Now during the off stage, the current coming from the inductor partially is charging the output capacitor and partially is going into the output load. So we got the capacitor acting as a buffer to absorb the excess current coming from the inductor. And again, if we look at the voltages, we can see that we got a 10 volt input and we got a 24 volt output this time. So the output voltage is higher than our input voltage. And again, if we look at our efficiency, we see about 5.7 watts of output power and 5.4 watts of input power. So we created something that is giving us more power than it's draining. So something's wrong here. It seems that LTspice is making some interpolation somewhere, and we're managing to get far more efficiency out of this circuit than we should be able. Now normally the circuit should absorb more energy than it's putting out, but hey, it's a Christmas miracle. Or Easter, something like that. So the final converter that I want to look at today is the Inverting Buck-Boost. Now what on earth can this be? Well, let's analyze a bit the schematic first. So as you can see, the components used are exactly the same as in the previous boost and buck converter. So again, we got our input capacitor, output capacitor, load, an inductor, a diode, and a switch. And again, we need to analyze the two cases, once when the switch is closed, once when the switch is open. So let's start with the first case. So we got our input voltage, positive in reference to ground, and we're using this voltage to charge our inductor. So we cannot have voltage going back from the diode. In this case, our input capacitor was the generator, our inductor was the load. In the second case, the switch has opened. We have no longer current flow coming out of our input capacitor, so we can neglect it. And our inductor will change from a load to a generator. So the direction of the current will stay the same, but the polarity on it will be different. So the current will go through our inductor, back through our output capacitor, and through our load. And then it will close through the diode. Now there's something interesting to notice here. Because of the direction of the current and the polarity of the voltage on the inductor, the output capacitor is charged in reverse. So our output voltage in reference to ground is negative. Both supplies that we analyzed until now had both input and output voltages of the same polarity. Both are positive. In this case, the input voltage is positive, but the output voltage is negative. This is where the inverting name comes from. This supply will provide an inverted output voltage in reference to the input. Now to finish the analysis, our output capacitor is a load, and in our first case, when we had the switch enabling current flow to charge our inductor, the output capacitor turns from load to generator. The polarity of the voltage stays the same, but the direction of the current will be different. So this time the output capacitor will be supplying our load resistor. So our load will have supplied to it both in the case when the switch is closed and when the switch is open. Now, how is the output voltage in reference to the input? So we know the polarity is different, but is it larger or smaller? Well, if we analyze the second case, we can say that the voltage on our generator, which is the inductor, is equal to the voltage on our loads. So the output voltage plus the diode voltage. Now, you may notice that one term is missing from this equation. A term that we used to have in our previous two analyses. That is the input voltage. So that means that our output voltage, in reference to the input voltage, can be higher or lower, depending on how much time we spent charging the inductor. So for the inverting buck boost, we can say that the output voltage in modulus can be smaller than our input voltage, or it can be larger than our input voltage. This is one of the things that makes the buck boost interesting. This is where the buck boost term actually comes from. It can either buck, so it can decrease the voltage, or it can boost. It can increase the voltage. But it's still an inverting topology, meaning that the output voltage will be the inverted of the input voltage. So again, we have same components as in our diagram, and let's fire it up. So we can see when we have our on and off times and the corresponding current coming from the input. So the current going through the switch, which is rising only when the switch is on, and then when the switch is off, it's at 0. Now we can see the same current going through the inductor. So the inductor is being charged in our on time, and then it's being discharged in the off time. And now if we look at the current going through our load and through the output capacitor, again the current is going in the other way through the output capacitor, and remove some of our extra traces. So although it's not very easy to see, the current from the inductor is charging our output load and the output capacitor when the inductor is being discharged, and when we're charging the inductor, the output current is coming only from the output capacitor. So again, we can see the output capacitor working as a buffer, absorbing energy in the off time and generating energy in the on time. Now let's see if the inverting buck boost is actually inverting. So we can see our input voltage, again static 10 volts, but our output voltage is minus 54 this time. The output voltage is inverted in reference to the input voltage, and because of the used duty cycle, it's much higher voltage than the input. So the absolute value of the output voltage is 5 times higher than the input in this case. Now let's see if we created a free energy device this time. So we can see that our input power is 7 watts and our output power is 5.8 watts. So this time we have lower than 100% efficiency. So we have a realistic circuit. Now let's try to make a voltage smaller than our input. So I will put a very low on time, and this time we can see that our output voltage is lower. So it has an absolute value lower than our input, roughly 1.7 volts compared to the input 10 volts. So with this circuit you will get inverted voltages compared to the input, but the absolute value can be higher or lower. And basically this concludes my video about the 3 basic non-isolated typical switch mode power supplies. Now there are a few more non-isolated topologies to analyze, but that's something for a different time. But for now, hope you got some useful information out of this. Thank you for watching, leave your thoughts in the comments, make sure to subscribe if you want to be up to date with my latest videos, and hope to see you next time. Bye bye.